So we're going to study 3 laws of motion in this section. They're not Newton's 3 laws, though. Okay? We've already taken a look at Newton's 3 laws. These are Kepler's 3 laws. Yeah. Okay, and these are going to be the laws of planetary motion. So we're going to take a look at what governs the motion of the celestial bodies that are out in outer space. We learn when we're younger, about like the galaxy and the solar system and gravity and how the Earth is not the center of the universe, and you learn all this stuff in your general science course. But today we're going to look at a little bit of the math that's really involved in it, and then some of the misconceptions that you may have from things that you actually learn when you're younger. So when you're a kid, and this question, it's funny because this question is asked, and there's a YouTube clip. Maybe I'll show it real quick. Should I show it?
Yeah.
It's like, all right, give me a second. I'm going to pause and show it. Yeah.
You just figure this out, or you just never do it?
No, I've done it before, but I've rarely done it like during class. So it was, I think it was like Harvard grads get asked questions about the solar system. Yeah, there it is. Harvard's grad seasons. And we're going to talk about this in a moment. I think this is the video. I hope it is. And I hope the sound is on. Is the sound on in this room? Really? An advertisement? I can skip. Come on. There we go. Okay. It's after the commencement ceremony, I think, if this is the right one. Unless this is actually, I hope it is the right one. Let's see. Yeah, it is. All right, so just listen to what they're going to ask. Come on, skip forward. It's just like, it's kind of sad because it's like such a misconception.
Time of the very best education. Students in our classrooms are failing to learn science.
All right, be quiet. Come on, skip forward. They're going to talk about, how people aren't like completely fully educated because of certain misconceptions.
Is that just something to do?
Yes, it has to do with Kepler's laws. Actually, so something you're going to learn today. That's why.
Oh, okay.
If it buffers, though, I don't know, guys.
Questions in astronomy.
Here we go.
Consider, for example, that the cost of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closest of the Earth to the sun during the season.
Most people think this is true, and it makes sense if you think about it. It's not true.
And it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse.
It's not
Even though
true.
the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carried with us the strong, incorrect belief that changing distance is responsible for the seasons.
I'll explain today what is responsible. We'll go over that. But the idea here, again, about common misconceptions, Kepler's laws, the things we're going to learn today, you're probably going to be like, oh, wow, I didn't realize that. Okay, so they're not really necessarily going to be intuitive in what you would think. We're going to prove the 3rd law and validate it, and then we're going to talk about orbital velocity. First, we have something called eccentricity in your Algebra 2 class this year. Or in your pre-calc, I forget. At some point, though, you'll talk about ellipses for sure. I think it's in your Algebra 2 trait class this year. And you're going to talk about the eccentricity of an ellipse. The eccentricity has to do with how stretched the ellipse is. If it's really close to a circle, it's pretty much 0. A circle's eccentricity is 0. As it gets further and further from being a circle and closer or more elliptical in orbit, it gets closer and closer to 1. It's some sort of a ratio, I forget. I think it's a ratio between the major and the minor axis, or the squares of them, but it has to do with the length of the horizontal part of the ellipse versus the vertical part of the ellipse. Okay, whereas, well actually, it's probably not a ratio because this would be 1, the answer, because this would be the same, 1 over 1. So maybe it's something they do differently. But as it gets stretched further and further, you're going to see eccentricity increase. The Earth's orbit is not really that elliptical, although the first law tells us that the trajectories of planets are elliptical in nature. Okay, so there's a small amount of eccentricity for the Earth, but you can see for Pluto, and do you remember seeing that in the solar system diagrams? A lot of the time, most of the planets were somewhat circular, and then you'd always see Pluto was this like planet that didn't follow the rest of the rules. Everybody else said, look at Mars. Mars is pretty close to a circle still, right? Look at that. It's not very far from the circle, 0.093. And look at the shape. But Pluto is always really exaggerated because Pluto's eccentricity is much greater than that of other planets. And yeah, and then we can go into the whole is Pluto a planet kind of deal.
It's a planet.
It was, then it wasn't, then it was. You know. But that's, right? At the end of the day, that's not even what's important, guys. If a planet cannot be inhabitable by humans, it sounds sad, but it's the truth, it's not really important to us. Jupiter's never going to be important to the Earth. I mean, unless for some reason Jupiter's like magnetic field caused our planet to have some sort of an alteration or something that changed us, right? Or their moons like flew out of orbit and like were coming toward the Earth. Like something crazy would have to happen for that planet to impact us. It's planets that are habitable by humans that are important.
No, it's the other way around. No, that is totally not the...
Yeah, I think it's the other way around. But still, that was pretty funny. So the idea, again, of the eccentricity, okay? It's elliptical, but it's not necessarily going to be obvious or noticeable. Now, the second part about this is that we should recognize that an ellipse has something called, God bless you, ×2? Okay. Something called focal points. Anybody ever hear of the word focal points before? Would you know how to explain it in terms of an ellipse, what a focal point is? Not like a focal point in your essay, what are you focusing on? Like the middle, but it's not. You're on the right track.
Aren't there like, I would just assume that there's 4, so there's, 2, so you have like the like farthest in the X and then the farthest in the Y, I guess?
You're on the right track, yeah. So he's thinking of what's called a major and a minor axis. An ellipse does have a major and a minor axis length, and one is horizontal and one is vertical. Like a diameter, but 2 different diameters, one this way and one that way. But focal points are like centers, but there's 2 of them. So imagine here is the sun, okay, in Pluto's orbit. Here is another focal point, but it's empty space. And a focal point is the idea that the center of an ellipse does not really exist. Okay, there really isn't a center if you think about it. Because for something to be defined as a center, it's a locus of points equidistant from the center of a circle. There's no real center to this. You have the major and the minor axis. For the Earth, though, here's the sun right here. And here's that other focal point right next to it. You can barely even see the difference there. I can zoom in to show you what I was pointing to, but you can barely see. If we look at there, see the point next to it? There's the other focal point. Because they're so close to each other, it's pretty much a center of the circle. So as you go from an ellipse, as you go from Pluto, which is an ellipse, to the Earth, which is close to a circle, the focal points get closer until they're pretty much on top of each other. When both focal points lie on top of one another, you have a circle. Again, if the focal points get so close that the ellipse becomes so circular that they're on top of each other, the focal points, you do have a circle in the end. That's what you have. So the Earth is really, really close to being a circular orbit. Okay, the focal points are so, so close. And we say close in a relative term. Obviously, they are a large distance, relative to our height or dimensions on Earth. But in the galaxy, there is a very small amount of space between the focal points that exist for the Earth's orbit around the sun. Okay? Let's take a look at this. Let's look at the second law. So the second one's interesting also. It again involves the sun. And on the left, you see the actual orbit of the Earth. On the right, another exaggerated form of that. When you were in middle school, you always saw the one on the right, where the sun was at one focal point and there was this crazy looking ellipse that was very slanted. Okay, it was squished down. It was oblate is the term. An oblate spheroid is like the Earth. The Earth's shape is not a perfect sphere. You'd say it's oblate because it bulges on the ends or the poles. So here we're going to see on the left, how many different sectors? You notice anything? How many different sectors do you see on the left? 12, representing, what do you think? Yeah, pretty much like 12 months of the year. Obviously, I know that the months are not actually the same length each, right? Some are 30 days, some are 31 days. But if you were to split up the time it takes the Earth to revolve around the sun, which is 1 year, 365.254 or 24 something. There's a weird way the Earth works. You know, like 10,000 years, you skip a leap year actually or something because of that extra decimal. But if you were to do that and split up the 12 even spaces, that's what it would look like. Which is really interesting. What kind of generalization? I mean, we can read the law and understand it, but look at the actual figure. What could you say? You get a question first?
Is it? I think I have a guess to why the seasons are.
Ah, okay. That's a whole other question, but all right.
Is it because the Earth turns?
What do you mean it turns?
Like, because how when it goes around,
It rotates.
It like spins and daily.
It rotates daily as it's revolving yearly.
Kind of towards the sun or whatever.
It has to do with, some sort of an angle. We'll talk about the tilt of the Earth. It does. Good, very good guess, I assume. Not, you didn't look it up. You guessed it.
Yeah, I didn't even look it up so far.
Good. No, I believe you. I just wanted to know because I was like, that's an interesting guess. Yeah, it does have to do with tilt. We'll talk about that. But back to this question. We have 12 different sectors, each most likely representing a 12th of the year. What do you notice, though? What's something you notice?
On the left side, they're like drastically bigger than the right side.
Yeah, on the left side, the distance traveled is drastically larger. Now, we don't know anything about the areas yet, and if you read the law, you're going to actually see something about the areas. But look at this length. Follow the marker, please. That length is much larger than that length, isn't it? I mean, this arc length right over here is probably half of this arc length all the way over here. So as a result, we could say that this covers more distance in the same time period because these are both representing a month.
So is that the reason why days are longer in the summer than in the winter?
Is that the reason why days are longer in the summer? No, it's not. The reason why days are longer, again, goes back to the tilt of the axis. Let me get back to that in a minute. Yeah, okay. But in this case, what's happening is this. The Earth is actually speeding up in this range. Now, it's not noticeable. Again, why? Because our orbit is very close to a circle, so this is still even exaggerated. So you're not going to actually feel it. But the Earth travels faster here than it does over here. Its tangential speed is faster here than it is over here. But what's interesting is its angular velocity, the way it covers ground, we have to consider if it were a circle, it would be similar to the rate on the right and left side. But again, we have an ellipse here, so it's not going to be a problem where we have angular velocity. So we can only look at the tangential velocity and say that this one is greater than this one. Well, why is that? The reason being is this. Second law tells us that if you take a line from the center of the sun to the center of the planet, so again, take the center of the sun to the center of the planet, and then sweep out an area, meaning this area right here that I'm shading, okay, that entire region right there, that area has to be equal to any of these other areas. Okay, these areas are always going to be the same.
So it's wider looking to us, the diagram is wider looking, but it's also looking to the sun. So
Sure.
all the areas are equal.
Exactly. So imagine you take a pizza and you slice it into 8 equal slices. They're obviously all equal, right? Because you can see it. It's very easy to cut it into 8 equal slices. But what if for some reason you cut one of them really, really narrow, right? It becomes a different size. Well, that's like doing it this way, but here's the thing. You're not cutting through the center now, are you? You're cutting like an ellipse. So as a result, some of these slices are narrower and longer, and some are shorter and stubbier. So depending on the different slice of pizza, it looks like a different area, but actually all the areas, all 12 of these areas have the same actual value. And what do you call that? You call that surface area usually, right? But area in this case, because we're looking at a two-dimensional plane. And we can see that over here. What it's saying is that if T1, the time it takes to do this, is equal to the time it takes to do this, then A1 is equal to A2. Then the areas are the same. Okay, if the same time period elapses. So if a day goes by, and it goes really fast because it's close to the sun, and then a day goes by when we're further from the sun and it goes slow, even though it goes slow and fast or relatively to one another, the same area is still covered by the planet in its orbit. Okay? All right. Now again, this is for all planets. It's not just for the Earth, for all planets. Take a look at the third and final law, and then we're going to do a lot. All of our math is going to come from this third law. Okay? So the third law tells us that the ratio, and this is interesting, the ratio of the squares of the periods, which is the period of revolution for the Earth, 1 year is period, 1 year for the Earth. The ratio of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So take a look at your first table insert, not the bottom one. Look at the top one for now. We'll see the Earth and we'll see Mars. And what we're going to recognize is that, yeah, this is how long it takes, the Earth to revolve around the sun. If you were to convert this, this would equal 1 year. Right? That's how long it takes us to revolve around the sun, 1 year. Well, take a look at Mars. It takes Mars, what looks like to me, a longer period of time, right? Mars is the fourth planet. We are the third planet. So we're following this like smaller radius, or the smaller circumference, if you will, this shorter path. Our ellipse is smaller on Earth. Mars is further out, so it's a bigger ellipse. Does that make sense? Right? Think about like a radius in a circle. So the Earth should take less time, and it does. The Earth's time is definitely less than Mars's, so we're good so far. We then look at the average distance and say, well, it looks to me like the Earth is closer than Mars. Well, that is also true because we are the third planet and Mars is the fourth planet. So our distance from the sun, on average, because remember, the Earth is sometimes closer to the sun and sometimes the Earth is further from the sun throughout the year. And that's, again, what we've been mentioning. But what we'll notice here is that our distance on average is shorter than that of Mars. But what's really, really intriguing is that if you square the period and then divide it by the average distance cubed, you'll get the same number or approximately the same number for both planets. Again, if you square the period of a given planet and then divide it by its average distance cubed for any given planet, it should be the same as or approximately the same as another planet. So look down at the bottom now. At the bottom, we just take our units. Instead of putting our units of period in seconds, we use Earth years. So how long is the period for the Earth? It's 1 Earth year. Mercury is like a quarter of an Earth year. Venus is 6/10 of an Earth year. Mars is almost 2 Earth years. When we get further out, what we're going to notice here now is take a look. Pluto, to go around the sun, it takes 248 years. It takes us 1 year because it's an Earth year, right? That's what we define as a year because we live on Earth. So for Pluto, to get all around that sun, it takes forever. But look how far Pluto is. AUs, astronomical units. Okay, I actually forget. I think it's the Earth unit. Yeah, it's the distance the Earth is from the sun. Okay, the distance the Earth is from the sun. So 1 AU is the distance the Earth is. Well, Pluto is 40 times further out than we are. 40 times further out. So as a result, it takes a lot longer time. Yet, what still happens, if you take a look at the period here and you square it, and you divide that by the cube of the average distance, you're still going to get approximately the same value for all the planets. Okay, so it's a law, and usually some people call this Kepler's constant. Okay, but it really depends on what your units are. Like this is Kepler's constant right here, but it's 1. Well, up in this other table, Kepler's constant was known as 2.9 times 10 to the negative 19, because our units were seconds squared per meter cubed, whereas here they're years squared per astronomical unit cubed. But the concept here is that if you go ahead and square it, divided by the cube, you get the same number for all planets. So if I gave you a random planet, you could go ahead and figure out what its period length is if you knew its average distance or vice versa. Why is this kind of interesting? And I say kind of interesting because you're probably like, it's all right. When did Kepler discover this kind of stuff?
A while ago.
Yeah, a whole long time ago, right? How did Kepler figure out that this was true for all planets? How did he know that Pluto was going to take 248 years? He didn't live for 248 years. He doesn't know. Does he have somebody like 3 lifetimes before him studying all the planets and their position in the sky with a telescope and monitoring it for the last 200 years? And I don't know the answer to this. I'm hypothetical saying this, right? But it's kind of amazing to think about this like random fact that t squared of r cubed is the same for all things in the galaxy. Okay, it's kind of like the beauty of physics when you look at this kind of stuff. You realize, oh my gosh, how does that just work out to be that number? How do certain ratios in nature always turn out to be what's called the golden ratio in math? Okay, so you learn about that kind of stuff. But this is one of those things, Kepler's third law. Now, we're going to take this concept and extrapolate from it a little bit. Before I go further, though, let's talk about the seasons. Now that we've talked about the 3 laws to answer the question, and Theo was on the right track, and he pretty much said the right thing there, that, yeah, you want to state it again?
So the seasons are based on what I'm assuming is like, because I guess because I know the south side of the planet, it's like summer when it's winter here, so I just, when the planet tilts, so one face of the planet is closer to the sun.
Getting more direct rays. Okay, exactly. So based on the tilt of the planet, sometimes the northern hemisphere gets direct rays. It's called insolation. Well, it's not really. Incoming solar radiation is a term I learned in middle school. It's not a real word, but it's like an acronym or 3 parts of 3 words. Incoming solar radiation. The angle of the rays hitting the Earth is closer to 90 degrees in the summer than it is in the winter. Okay, you also, as we talked about earlier, because of the rotation of the Earth and because of the tilt, get longer periods. So for example here, when we are in the summer, we are actually further from the sun in the northern hemisphere. In the northern hemisphere in the summer, we're further from the sun, which you wouldn't necessarily believe. So for us, so this is for northern hemisphere. For the southern hemisphere, it's the opposite. So yes, had that person been answering the question in the southern hemisphere in that video, they would have been coincidentally correct that that was a correlation, but not causation. The distance from the sun does not cause the seasons. It is correlated directly in the south, in the southern hemisphere. In the southern hemisphere, yes, in the summer they're closer, good for them. But that's not the actual cause of it. So correlation is not always causation there. So in this case, we have, again, summer here, oops, and winter over here. Again, because of the tilt of the axis, because of the tilt. So how do you suppose the diagram should look if we're going to think about summer versus winter? There's 2 M's in there, I swear, in summer. What's the tilt going to look like? What would I have to do to think about this?
The tilt of like the Earth.
Yeah, the angle is 23.5 degrees, I can tell you that, but what should it look like?
I would say like when it's summer, the tilt is more like the northern, like where we are is more like this.
Yeah, so like that. This is the North Pole, and this is the South Pole. This is the equator right there. Okay, it's exaggerating the tilt, but look, the northern hemisphere is getting the direct rays from the sun. The southern hemisphere, though, is not. And that's why certain parts of the southern hemisphere in the winter, well, in their winter, let me just go back. The northern hemisphere, because I'm talking about the southern hemisphere, it's going to confuse you. In the northern hemisphere, in our winter, there are days where there are 24 hours of darkness. And that occurs over here. And take a look. Doesn't that make sense? Look at the sun's rays. On the left-hand side of the sun, all the direct rays are going to the southern hemisphere. So there's a shadowed region. There's a region over here that doesn't get any of the sunlight at all. And in the depth of winter, on December 21st, on our shortest day of the year in the northern hemisphere, the certain region above a given latitude toward the North Pole will get 24 hours of darkness. And a certain region in the southern hemisphere will get 24 hours of light. It's above a certain ring. I forget what it's called, but it's like an Alaska. Part of it is in Alaska for sure, because there's certain parts of Alaska where you'll get full days of light and full days of dark. But it has to do with the tilt. That's the reason for the seasons. Okay, the tilt. So we can see that when we're in winter, the southern hemisphere is getting all the rays. When we're in summer, we are getting all the rays. And obviously, it's the opposite if you live in the southern hemisphere. Okay? Now, let's look at the third law and prove it using Newton's laws. Okay, so we're going to start with Newton's law of gravity, and we're going to set it equal to our centripetal force law, because that's what's providing it. Remember, how does a planet stay in orbit? A planet stays in orbit because of centripetal motion, but really, we have to think about the fact that that's provided by gravity. So let's start by thinking about our 2 formulas. Okay, we've got centripetal motion, which is mv squared over r. Why am I using m1? Why am I using M1 and not M2? Look at the definition of M1 and M2 and explain why I used M1 in this formula. Remember, this is circular motion we're looking at. Again, we're making a huge assumption, right? That this ellipse is really pretty much circular. That the elliptical orbit is pretty much circular to do this. And why would we be using M1?
Because we're trying to find the acceleration of the planet, not the force of acceleration of the planet, not the sun.
Yeah, we're trying to find the centripetal force, not acceleration, right? On the planet. Okay, on the planet. Now that force is exerted on the planet as a result of gravity, as a result of the pull from the sun. So now we can write our gravitational law. Mass of the Earth times mass of the sun. Let me put my g in the front. Now remember, that g that goes in the front here can go in the numerator, or it can go in front of the entire thing. It's the same thing. If I put the g out front or in the numerator, it's the exact same thing. So gm1 m2 over r squared. That's what's providing the centripetal force. Well, if the centripetal force is provided by gravity, we can do what to those equations? If they're equal to each other, because the one is providing the other. What can we do to equations if they're equal to each other? If they're equal.
Like if you're setting FC equal to FG.
Yeah, set FC equal to FG. And what do we get?
We get M1 to VT squared over R equals G M1 M2 over R squared.
Okay, keep going.
Can you cancel out M1?
Yeah, cancel whatever you think is algebraically true.
M1 and then I know about R because it's R squared.
So what can you do then?
Cancel out one of them. And then
Correct.
use
See
R.
what I did? Just drop off the exponent there so you do it. Go ahead. What do you end up with?
You end up with VT squared equals G M2 over R.
Now, this is the next part. We're gonna go from this step later to another law, an orbital velocity law. So keep this in mind. But now what we're gonna do is this. We're gonna pause for a second and we're gonna think about, well, what is velocity for an object in circular motion? We're making a huge assumption right now that this is a circle. It's not an ellipse, we're saying. Okay, it's a big assumption to make, but it does help us prove this true. Because again, the Earth is so darn close to being a circle. What do we know about the velocity of an object in circular motion? You did it with your lab when you were spinning the stopper. How did you calculate the velocity that you were spinning with? You measured time, right? Remember in the lab you measured the time it takes? And then what else did you need? What other piece of information? How do you calculate speed of something moving? How do you calculate speed of something moving? You need two pieces of information for speed. What are they? Two pieces. Benno? Careful. Distance and time. Okay? So velocity and speed are similar things, right? So if we're looking for speed here, because VT, remember, is really the tangential speed, even though we have V for velocity, we need the distance traveled. Well, if it's going in a circle, what distance do we call that? What's the name of the circular shape traveled when we're going to circle? Yeah, 2 pi r, or circumference. Very good. So this is really 2 pi r over t. I'm going to replace that. And then the rest remains the same. Again, velocity is really distance over time, or in this case, speed, sorry, I should say. Speed is distance traveled over time. The distance you traveled is one circumference. Assuming it's a circle again, right? We're making that assumption because it's so close to it. So we have 2 pi r over t. That whole thing is squared. Let's do a little bit of algebra here now. So stay with me. I'm going to do a little bit of algebra. We have 4 pi squared r squared over t squared equals g m2 over r. So obviously all I did was what? Expand it or square everything. Expand is the right word, yep. I expanded it or I squared everything inside of the parentheses, which is what I should do. Then what I'm going to do after that, I'm going to go ahead and move t squared over to the right-hand side by multiplying it up. Move r squared down here by dividing by r squared. Remember, you can always move things diagonally. I'm going to take gm2, and since it's in the numerator, I'm going to divide it on both sides, so that's going to end up over here. So I'm literally just switching those two. So I'm going to take r squared, move down here, and then flip-flop these two. Okay? So again, let's move r squared. And we can always do this. This is always true because this is a numerator. To get rid of it, you would divide by r squared on both sides, which really takes it and just puts it down here. This is going to get switched with this. So I'm left with 4 pi squared over gm2 equals t squared over r cubed. Well, t squared over r cubed is what we've been talking about the whole time. A moment ago I told you that if you take the time period of revolution and square it over the average distance from the sun and cube it, you'll get the same ratio for every planet. Well, it's true because look, aren't these numbers over here all constants? The number 4, you know what it is. It means 4. Pi means pi. G means 6.67 times 10 to the negative 11. M2 is the mass of the sun. That is a constant. It is not changing. It's not a function of the planet itself. So as a result, this is a number. You can calculate it. You can determine it right now. If you did calculate it, you know what you would get? You would get this number from way earlier, from this top table. Oops, in the previous slide, actually, I guess. In the previous slide, there was a table on the top. And we had a ratio of t squared over r cubed for Mars and for Earth, the first table in the previous slide. I calculated t squared over r cubed in the third column. That's what this turns out to be. So because t squared over r cubed is really just a bunch of constants multiplied and divided, these are never going to change for every planet. So if I'm on Earth, if I'm on Pluto, if I'm on Mars, if I'm on Mercury, this is true for all of them because this is a constant in the galaxy. The mass of the sun is a constant, gravity is a constant in the galaxy, and so is 4 and pi. So this is true, the third law, that we could take the square of the period of a planet over its average distance cubed and get the same ratio for all planets. Okay. Talk for a moment about satellites. We spoke about them. We talked about satellites in the previous lesson, and we defined satellites. We said, traditionally you think of satellites as man-made satellites, like these, metallic shiny things that orbit above the Earth to give us cell phone signals and, whatever else, telecommunications we need. But satellites in general are anything that orbit a central object. Okay, so the moon is a satellite of the Earth is a satellite of the sun. So if we want to think about this for satellites, how do they actually work? How do they stay in space? And it's actually really interesting. A satellite is constantly falling. Bear with me for a second. I'm talking about a specific type of satellite. So traditionally, we talk about geosynchronous satellites. Geosynchronous satellites move with the Earth. Here's the Earth, okay? It's rotating. It rotates once a day. As it rotates, use the satellite. My pen, right? It moves with it, with the same angular speed. Right? Look, it covers 15 degrees per hour, totaling 360 degrees per 24 hours. Right? I just did some quick math. I made 360 degrees for the day in 24 hours. So 15 degrees of rotation every hour. That's how fast the Earth spins. Angular speed. But because the satellite is further out than the sun and the Earth, it has a higher tangential speed. Right? Look at the path. The satellite travels this huge path in one day. The Earth travels a path, technically the outer part of the Earth, the surface, travels a path that's equal to the radius of the Earth times 2 times pi each day. Whereas the satellite's all the way out here. Look at the bigger orbit, right? The satellite. So the satellite travels at the higher tangential speed because it's further out. But they move in tandem. So they move at the same angular speed the whole time. But the question is, how does it stay in orbit? Well, a satellite is launched. Okay, and I'll show you a diagram so I can explain it, but I'm going to talk about it as I go. The satellite is launched. And it's launched at a specific angle with a specific velocity, such that it falls 5 meters for every 8,000 meters it travels horizontally. So imagine you could fire a bullet that would travel 8,000 meters and fall 5 meters. What would happen? It would actually follow the curvature of the Earth perfectly. And imagine it just kept falling, and it kept falling, and it kept falling. You kept providing with some initial velocity. Or you got it out to space, and you got it up to the right velocity, where when it stays at that velocity, it falls 5 meters every 8,000 meters. Well, why can it stay at that velocity if it's in outer space? Because there's no friction there. There's no atmosphere. You go above the atmosphere, suddenly these satellites, can travel with a simple rocket booster that fires it, and then the rocket booster turns off. An object in motion will stay in motion. So it's continuing to stay in motion. The outside force that's acting on it is Earth pulling it toward it. Well, it's falling, and it's falling, and it's falling, but it maintains that velocity that it had. So it can stay in geosynchronous orbit with the Earth. It moves with the Earth. As the Earth rotates on its axis, this satellite is falling, but with the same exact curvature of the Earth. They're like concentric circles. Have you heard that term before? Concentric in geometry? Two circles that share the same center. Right, here's the Earth, and here's the satellite. The satellite is simply falling, but it keeps falling in such a way that it falls into orbit, and it continues to fall into orbit 5 meters every 8,000 meters that it travels horizontally. So it's really just necessary to get it out there, and then it will maintain that motion. Okay, it'll maintain that motion. Let's quickly look at the actual velocity of a satellite based on its elevation. We can see what the satellite's velocity would be necessary. Start with the same thing we did before. We're going to set centripetal force. I'm going to do it. I'm going to jump the gun though a little bit, right? We're going to set centripetal force equal to gravitational force. The same way we did last time. We're going to cancel again. And we're going to end up with this equation. This is the one that I was mentioning earlier. Now recognize that M2 is the mass of the central object. If you need to highlight that, please do so. Okay, it's the central object's mass. The mass of the central object. That's M2. Now, obviously for us, that happens to be the Earth, and the outer object would be the satellite. Okay, the satellite would be whatever the satellite is in orbit. That's the satellite's mass. That's M1. It's not the same as earlier. Earlier we had the Earth and the Sun. Now we have a satellite, and we have the central, God bless you, the central object, which is really the Earth. So as a result, we get this relationship. We can solve for V. Square root both sides, please. Oops, didn't mean to have that on. Square root both sides, please. And you'll get your solution for orbital velocity. That gets rid of the square, and that's our solution. So if we have the gravitational constant in the universe, which we do, if you know the mass of the central object, and you know how far it is, r is distance now, distance from center to center. So if you have the Earth, you need the radius of the Earth. Let me draw it out again. We did this last time, but let me make sure it's clear. So if you've got the Earth right here, and you've got the moon out here, the distance from center to center is from that dot to that dot. So we had to add the Earth's radius plus the gap plus the moon's radius. Now, the moon's radius and that gap is pretty insignificant when compared to the Earth's radius. So you could see assumptions made that like you don't even have to encounter them or account for them. But those are the three things that you would plug in for R. You'd sum these three together, right? RE plus the gap plus the radius of the moon is really what R is. R is that full distance. That's the denominator. Remember, M2 is the mass of the central planet. So what's interesting to notice, what has no effect on this? Which is not intuitive at all. There's something that has no effect on the velocity, yet it should, if you think about it. What is it? Come on.
Could it be the mass of the other planet?
Yeah, shouldn't the satellite's mass have an effect? Like if I'm heavier, we always hear like, oh, if I'm heavier, it should have an effect on how I orbit the planet or how I move through the air.
Is that like the experiment that you showed us with the feather?
Yeah, part of that is, that's exactly right, Katie. The fact that mass does not affect the rate at which you fall to the Earth. Remember, the rate at which you fall to the Earth is negative 9.81 meters per second squared. That's the acceleration due to gravity. So this satellite is falling to the Earth at some rate. It doesn't matter what mass the satellite is. You know what? The mass of the satellite does affect how much rocket fuel you need to get up there. Right? Think about that. While you're on Earth, before you get up to this area where there's no friction, you need more fuel to get you there because it's a heavier satellite. So a smaller satellite takes a lot less to get into orbit. But once they're in orbit, it doesn't take much more than the heavier satellite or the lighter satellite to run the heavier satellite. Okay, so the mass of the satellite has no effect on its orbital velocity. Orbital velocity is independent of the mass of the satellite. That's how you would say it, right? Independent of means it does not depend on. Okay? The orbital speed is independent of the mass. Take a little break. Come back. We're going to do a lab.